Okay, so again, in Chapter 2, we said that the empirical formula was the smallest whole number ratio. So, for example, we said that something like C6H12O6, well, we said that's not an empirical formula. That would be a molecular formula. The empirical formula would be CH2O, because that's the lowest whole number ratio. Now, remember what this is telling us. This is telling us, this empirical formula, that for every one of these compounds, I get 1 mole of carbon per 2 moles of hydrogen per 1 mole of oxygen. So it's showing me, a chemical formula shows me the ratio of moles, right? So we're comparing 1 mole to the other mole to get that ratio, an empirical formula. And so in order to calculate an empirical formula, at the very end, that's what you need. You need a comparison of the number of moles of the substance so the empirical formula is all about trying to get to that moles. Are both those for you? Oh, you want to take it to them? Go ahead, man. We'll wait. Yeah. Can't let something like that go to waste, man. Just surprised that an AC kid has a boyfriend, to be honest with you. I got a question for you. This came up yesterday. Would you eat lab-grown meat? Okay. Just wondering. You know, it's not from an animal. It's literally lab-grown. Yeah. When's the last time you had meat? Was it? So you were in, you're a junior. So you were in what, 8th grade when you? Ish. Interesting. All right. So the empirical formula, we're trying to get that mole ratio, right? Moles to moles. So you can sort of see what we're going to do here step by step. And it depends on where you start. You may start somewhere along this map here. You don't necessarily have to start with the percentage of the elements. So we did percent composition, right? We talked about how to calculate percent composition. And that percent composition was by mass, right? We said you can also do percent composition by moles. You don't see it as often. Make sure you know which one you're talking about. If we're doing percent composition by mass, then we can take our percentage, and if we assume that we have 100 grams of that compound, then our percentage becomes our grams. And we'll see an example here. But remember, we're trying to get to a ratio of moles. So compare moles of compound A to moles of compound B, and then that'll give us our mole ratio. So we can't stay at grams. I have to convert to moles. And we do that by using molar mass. Now I have how many moles are actually in the substance, but I want a ratio of moles. Because that CH2O, that doesn't tell me that I have exactly 1 mole of carbon, 2 moles of hydrogen, 1 mole of oxygen. What it tells me is that when I look at the ratio of moles, for every 1 mole of carbon, I have 2 moles of hydrogen. It could be a very, very small amount. You know, you're not necessarily always going to have 1 mole of the substance. And so at the very end, we need to get a mole ratio. And the way that we do that is you just divide through by the smallest. You don't have to. Whenever you're doing a ratio, you don't have to divide through by the smallest. But that's how you get a ratio that people understand. Like if I tell you there are 0.7 boys for every 1 girl, that doesn't really make a whole lot of sense to you, as much as there are 1.2 girls for every boy. I mean, that makes a little more sense to you. That, okay, there's more than 1 girl per boy in the class. So that's why we usually divide through by the smallest and not the other way around. So let's go ahead and take a look at one of these. Sample exercise 3.13. Ascorbic acid, which is vitamin C, contains 40.92% carbon, 4.58% hydrogen, and 54.50% oxygen by mass. What is the empirical formula? Okay, so let's go ahead and jot down what we have here. One of the big things with the AP curriculum that we'll try to work on throughout the whole year is presenting your data, presenting your work. So this is a big thing, because if you present your work and it's all over the place, it doesn't look like you know what you're doing. It looks like you have no idea and you're just putting numbers down, hoping that somehow you get to the answer. But if everything is organized and there's a flow to it, it's a lot easier to grade, which that's what you want to do, make things easy for the grader. But two, it looks like you already knew what you were doing, and so you're just sort of laying out your argument for your answer. So keeping things organized is a pretty important idea. All right, so let's start out. We have 40.92% of carbon. We have 4.58% of hydrogen, and then 54.50% oxygen. So that's percentages. The first thing we're going to do is convert that to grams, and we're just going to assume that we have 100 grams. So that means that I have 40.92 grams of carbon. I have 4.58 grams of hydrogen, and I have 54.50 grams of oxygen. So now I have grams of each. Sometimes in empirical formula problems, you start with grams. No problem. Remember, we're just trying to get to moles. So if I start with grams, I'm going to start right here. I just go from grams to moles. All right, so I am going to convert from grams to moles. So for every 1 mole of carbon, I have 12.01 grams. For every 1 mole of hydrogen, I have 1.008 grams. And for every 1 mole of oxygen, I have 16 grams. And now that's going to give me moles. Moly. So that's 3.40-ish. I get about 4.54. That's moles of carbon, moles of hydrogen, this is also 3.40 moles of oxygen. So if I had 100 grams of this substance, that's how many moles of each substance, of each element I would have. But what I want to know is the ratio, so I'm going to divide through by the smallest, which happens to be 3.4. So I get 1 carbon for every 1.33 hydrogens and every 1 oxygen. So that's my ratio. For every 1 carbon, I get 1.33 hydrogens and 1 oxygen. So, bless you, my empirical formula becomes C1H1.33O. But of course you can't have 1.33, right? So we have to multiply it by something to get it to be 0. So here's sort of the general rule. 0.9 and above, so if it's 0.91, 0.92, 0.93, you can round that up. So if I had like 2.92, I could round that up to 3, right? 0.0 and below, you can round down. So if I had 5.06, I can round that off to 5, right? 5.15 you can't round, because that's not 0.0 or below. So let me jot that down here. So over here by the empirical formula, rounding 0.9 or above rounds up, 0.0 or below rounds down. So here, this is 0.33. Obviously, I can't round it up or round it down, so I have to multiply it by something. So what do you think I should multiply it by? 3, yeah. So if I multiply by 3 here, let's see what I get. I get carbon 3, right? What's H going to be then? Oops. 4, yeah. And then O is going to be 3. So there's my empirical formula. I'm just going to jot that down. The empirical formula is C3H4O3. Any questions on that? Alright, then let's talk about molecular formula. So there's usually a whole number ratio between the molar mass of the molecular formula and the molar mass of the empirical formula. And let me show you. We're going to do sample exercise 3.14 here. So mesitylene, a hydrocarbon found in crude oil, has an empirical formula C3H4. So here's the empirical formula right there. We have an experimentally determined molecular weight of 121. So in other words, the molecule weighs 121 AMUs. We know that. What is the molecular formula? So what we want to know is, if this is the empirical formula, how many times does the empirical formula go into the molecular formula's weight? So I can say that the, what did I say up here? Some whole number multiple, it's equal to the molar mass of the formula divided by the molar mass of the empirical formula. So we know that it weighs 121. The empirical formula I think that's right. My brain's not in calculating mode yet. So the empirical formula weighs that much. So when I do this, when I calculate that out, I get a number of 3. That's right over here. And so that means that 3 empirical formulas will go into the molecular formula. So in other words, I've got C3H4, and I'm going to multiply by 3. So I end up with C9H12. So that's the molecular formula. Any questions on empirical or molecular formula, the calculations? Okay.